Now, we shall apply the same concept into Experiment 5. In Part A of Experiment 5, an equilibrium system of iron 3 plus ion, thiocyanate ion, thiocyano iron 3 complex ion is being studied. Iron 3 plus ion is yellowish-brown in color, while thiocyano iron 3 complex ion is blood red in color. Initially, the equilibrium is blood red in color as shown in the picture. When the equilibrium system is being disturbed by increasing concentrations of iron 3 plus ion, the system will respond to reduce the concentrations of iron 3 plus ion by shifting the equilibrium positions to the right. This will result in concentrations of thiocyano iron 3 complex ion to increase and concentrations of iron 3 ion and thiocyanate ion to decrease in new equilibrium. As amount of thiocyano iron 3 complex ion is higher, darker blood red color is observed in new equilibrium. For the same equilibrium system, if the system is disturbed by increasing concentrations of thiocyanate ion, the system will respond to decrease the concentrations of thiocyanate ion. The system will shift the equilibrium positions to the right to decrease the amount of thiocyanate ion. This will result in amount of thiocyano iron 3 complex ion to increase and amount of iron 3 plus ion and thiocyanate ion to decrease in the new equilibrium. As the amount of thiocyano iron 3 complex ion increase, darker blood red color will be observed in the new equilibrium. What happens if the concentrations of reagent is be reduced? For the same equilibrium system, the concentrations of iron 3 plus ion can be reduced by adding some sodium hydroxide solutions into the equilibrium system. As iron 3 plus ion can react irreversibly with hydroxide ion to form solid iron 3 hydroxide, the amount of iron 3 plus ion in the equilibrium system is therefore being reduced. Hence, the system will respond to increase the concentrations of iron 3 plus ion by shifting the equilibrium positions to the left. This will result in lower amount of thiocyano iron 3 complex ion and higher amount of iron 3 plus ion and thiocyanate ion in the new equilibrium. As thiocyano iron 3 complex ion is lower and iron 3 plus ion is higher in the new equilibrium, the solutions will therefore turn yellowish brown. In color and water. The equilibrium system is purple in color. When the equilibrium system is placed in the ice bath, the solution turns to pink. What does this imply? It means that when the equilibrium system is disturbed by lowering the temperature, more hexa-aqua cobalt 2 complex ion, which is pink in color, is being produced. Hence, the equilibrium position is shifting to the left. Now, shall we deduce whether the reverse reaction is exothermic or endothermic? When the temperature of the equilibrium system decreases, the system will respond to increase the temperature by releasing some heat. Hence, exothermic reactions is favored, and this implies that reverse reactions is exothermic. When the equilibrium system is being placed in the warm water bath, the solution turns blue. This means that more tetrachlorocobalt 2 ion is being produced when the equilibrium system is being disturbed by increasing the temperature. As more tetrachlorocobalt 2 ion is being produced, it means that the equilibrium position is shifting to the right. So, is the forward reaction exothermic or endothermic? When the equilibrium system is disturbed by increasing the temperature, the system will respond to decrease the temperature by absorbing the heat. Hence, endothermic reactions is favored. and the forward reaction is therefore endothermic. For a reactions in equilibrium, an equilibrium constant expression K can be written for the reaction. For example, an equilibrium of A mole of A reacts with B mole of B to produce E mole of E and D mole of D. The equilibrium constant expressions can be written as Kc equal to concentrations of E raised to the power of E multiplied with concentrations of D raised to the power of D over concentrations of A raised to the power of A multiplied with concentrations of B raised to the power of B. The C on the equilibrium constant represents concentration, while the square bracket represents the concentrations of each substance. Based on the example, it can be seen that the numerator of the equilibrium constant expression is the product of the concentrations of all the substances on the product side of the equilibrium equation, with each raised to a power equal to the coefficients in the balance equation. The denominator is similarly derived from the reactant side of the equilibrium equation. Another example is dinitrogen tetroxide dissociate to form nitrogen dioxide. The equilibrium constant expressions Kc can be written as Kc equals to concentrations of nitrogen dioxide raised to the power of 2 as the coefficient in the balance equation for nitrogen dioxide is 2 over the concentrations of dinitrogen tetroxide. The magnitude of K indicates how far a reaction proceeds towards product at a given temperature. For heterogeneous equilibrium, example solid calcium carbonate dissociate to form solid calcium oxide and carbon dioxide gas. The equilibrium constant expressions Kc is expected to be Kc equals to concentrations of calcium oxide multiplied with the concentrations of carbon dioxide over the concentrations of calcium carbonate. However, the concentrations of pure solid and pure liquid shouldn't be included in the equilibrium constant expressions because the concentrations of pure solid and liquid is constant value. Hence, the equilibrium constant expression should be just Kc equals to the concentrations of carbon dioxide. Now you may pause for a while to attempt the questions. What's the applications of Châtelier's principle? In industry, manufacturers' goal is to maximize the product in a reaction. However, not all reactions can go to completions to give 100% yield. However, by applying the concept of Châtelier's principles, the manufacturers can maximize the yield for reversible reaction. For example, in Haber process to produce ammonia, the manufacturer's aim is to maximize the amount of ammonia produced. To maximize the amount of ammonia produced, it means that the amount of ammonia must increase in the new equilibrium. To do this, the equilibrium position must shift to the right. For equilibrium position to shift to the right, the system must respond to decrease the concentrations of nitrogen gas or hydrogen gas. Hence, initial equilibrium must have been disturbed by increasing the concentrations of reactant of nitrogen gas or hydrogen gas. The manufacturers can also increase amount of ammonia in new equilibrium by manipulating the concentrations of product ammonia. How does this work? To increase the amount of ammonia, the equilibrium positions again must shift to the right. To shift the equilibrium positions to the right, it means that the system responds to increase the concentrations of ammonia. Hence, the initial equilibrium system must have been disturbed by decreasing the concentrations of ammonia. Manufacturers can also maximize the yield of ammonia by changing the temperature. Again, to increase the amount of ammonia, the equilibrium positions must shift to the right. This means that the system must favor exothermic reaction, releasing heat to the system to increase the temperature. Hence, the initial equilibrium system must have been disturbed in lowering the temperature.